Okay, so in this screencast, we dare to apply what we've learned. We just dare to apply what we've learned. What do I mean? Oh golly, let's try black. Let's suppose that dy dt is k times y, and that y is y naught when t equals 0. Let's suppose we have a physical situation where the rate of change of some quantity is related to how much of that quantity there is. So this is a scenario where populations may grow this way. If there are more people, then that affects how many people can make more people. Maybe this is how money grows, because the more money you have, the more money you can have, kind of a thing. And this part is the initial condition. The initial condition just establishes at the beginning of time, there is some known amount, some known number of people, some known amount of money, what have you. Number of bacteria, it could be almost anything. And so this is what's going to help us choose from among all the antiderivatives, because remember, when we anti-differentiate, we get a plus c. We want one, not all of them. So let's solve. There's nothing terribly difficult about this solve. K is some number. The variables in the problem are y and t. So we have a y part and a t part, and we rewrite. We separate the differential equation. This means that the left-hand side is the natural log of y, and the right-hand side is k times t plus some constant. Well, what does that mean? That means that y is e to the kt plus a constant, sorry, absolute value of y. What does this plus mean? Well, this plus means that this is an e to the c and an e to the kt. E to the c is some number a, and because that a can be either positive or negative, we can remove the absolute value. This, because a can be any real number, this is what, oh, so sorry. This is what lots of people refer to as the law of exponential change. Now, truth be told, the law of exponential change is really this differential equation, but this differential equation always ends up looking something like this. This is what occurs, let's do a quick side note here. This occurs whenever the rate of change is proportional to the amount present. Anytime you see language about the rate of change being proportional to the amount present, you are dealing with exponential change. So let's pretend there are bacteria, and bacteria are growing in a way that is proportional to the number present. And this is a dead giveaway that we're dealing with exponential change. After 3 hours, there are 10,000 bacteria. After 5 hours, there are 40,000 bacteria. I want to know how many there are at 6 hours. And this is relatively straightforward to do. So we know, because we're growing at a rate that is proportional to the number present, that the number of bacteria is some fixed number times e to the kt, and we have this information, and we have this information. The question is, what do we do with this information and this information? And the answer is we divide. We divide these by those. 40,000 divided by 10,000, AE to the 5K over AE to the 3K. And this can be solved. We can find out that K is the natural log of 2. That's algebra. So what do we know? We know that 10,000 is A times e to the 3k. And this can be solved to figure out that A is 1250. This is the Y0. This is the Y0. This is the number of bacteria when the stopwatch started. But what are we looking for? We're looking for what happens at time equals 6. So at t equals 6, the number of bacteria is A times e to the kt, and this turns out to be 80,000. And all of your exponential growth, exponential decay, all the stuff you did in Algebra 2 stems from this. But I would like to look at one other application before we're done here. I'd like to look at Newton's law of cooling. Newton's law of cooling states that T minus T sub s is T sub 0 minus T sub s times e to the minus kt. Now, everybody just accepts that, and then they go on to the question. The casserole comes out of a 350-degree oven and is placed in a 70-degree room. 30 minutes later, the casserole's 150 degrees. How long till it's 100 degrees? And everybody misses the fact that this is law of exponential change, right? So if we imagine that the room is 70 degrees, and we think not about the temperature of the casserole, but how far the casserole is from 70 degrees, this is the law of exponential change. This is how far the temperature of the casserole is from 70 degrees. T sub s in these questions is the temperature of the surroundings. So this is the difference between the initial temperature and the temperature of the surroundings. So this is a variable that represents how far the temperature of the casserole is from the temperature of the room. It'll never go below the temperature of the room. And this is the difference originally between the temperature of the casserole and the temperature of the room. So this is the initial, this is the capital A, so to speak. So what do we know? We know that T minus 70 is 350 minus 70 times e to the negative kt. Why negative? It just reminds us that the temperature is going down. K ends up being a positive number in this case. We know that after 30 minutes, the temperature is 150 degrees, which means that 80 is 280 times e to the negative 30k. And this can be solved. This can be solved to figure out that k is 0.041759. Well, what are we looking for? We're looking for the time when the casserole is 100 degrees. Well, when it's 100 degrees, 100 minus 7 will be 30 equals 280 e to the negative 0.041759 times t, and that can be solved to figure out that it happens 53 minutes after we take it out of the oven, or 23 and a half more minutes after it's 150 degrees. I hope this is helpful. I went just beyond 10 minutes. I hope you haven't clicked away yet. We'll see you in class.